this video, we're going to look at indeterminate forms and L'Hopital's rule. We are familiar with arithmetic expressions that are well defined. For example, we know that 3 multiplied with 5 equals 15. We're now going to look at certain expressions or forms that provide us with arithmetic inconsistencies. For example, let's say that instead of 3 times 5, I now look at 0 multiplied with infinity. So, we remember from arithmetic that multiplication by 0 of any real number, for example, say 0 times 5, that equals to 0. So 0 is going to dominate this expression of this product and is always going to turn out to be 0. However, say that I now replace the 0 in the 0 times infinity by 5, and if you have infinity and multiply it by 5, you're only making your infinity bigger, so this expression equals to infinity. So we notice that this form here, 0 times infinity, is going to be an indeterminate form, because we can't really determine which of the two factors, namely 0 and infinity, should dominate the expression. Should 0 take precedent and so the result should be 0, or should infinity take precedent in this product and thus the result should be infinite? So therefore this expression is going to be one that is indeterminate. Namely, when we compute the limit and when upon evaluating we run into this indeterminate form, the answer to this limit could turn out to be anything, not just 0 or infinity, any number in between, negative numbers, or the limit might also not exist. There are other such indeterminate forms. For example, say 0 over 0. Again, we encounter this duality, namely, if I replace the denominator, the 0 in the denominator, by 5, 0 divided by 5, that's going to be equal to 0. The 0 in the numerator thus determines the answer. If, however, I replace the 0 in the numerator by 5, then 5 over infinity will be some sort of infinity. I'll put it in quotation marks. 5 over 0 will be either plus or minus infinity. We'll be dealing with this explosion to plus or minus infinity. So again, should the 0 in the numerator or in the denominator dominate, and depending on that, depending on how the numerator and the denominator of a function act, you will get maybe 0, maybe infinity, or also any other number in between. So 0 over 0 is another indeterminate form. Similarly, infinity over infinity is another indeterminate form. Should the infinity in the numerator dominate, and therefore the answer, say infinity over 5, would be infinite, or should the infinity in the denominator dominate, and so 5 over infinity will give us 0. So this is a third indeterminate form, and these are the main forms that L'Hopital rule is going to deal with. So now let's determine which of the following forms are indeterminate and which are determinate. So we've already realized that infinity over infinity, 0 over 0, as well as 0 times infinity were indeterminate forms because we had this duality whether the 0 or the infinity should dominate the expression. So let's try to think of the other forms. For example, this 0 over 0. What happens if I replace the 0 in the exponent by 5? 0 raised to the 5th power is 0. On the other hand, if I replace the 5 by 0, I get 5 to the 0th, which is 1. Again, we encounter this duality, so this happens to be an indeterminate form. Similarly here, if I have 1 to the 5th, that's going to be 1. 5 to infinity, that's going to be infinity. So we get two different answers depending on whether 1 or infinity takes precedent into this rule. So again, this is an indeterminate form. as opposed to infinity raised to the infinity power, well, I'm only multiplying infinity with itself infinitely many times, if you want to think of it this way. So this is a perfectly determinate form, and the answer is just infinity. How about if I take infinity and divide it by 3? Well, that's still going to give me infinity. So again, this is a determinate form, as well as infinity times infinity. That too just equals infinity. Now, what is 1 over infinity? Well, we saw that this is a perfectly defined form, namely 1 over infinity in the limit equals to 0. Think of the graph of 1 over x. As x goes to infinity, that approaches the horizontal asymptote of y equals to 0, and therefore we have that 1 over infinity is 0. In fact, you should try to remember that 1 over plus or minus infinity, we had this notation, we're abusing it, and that gives us 0. And then depending on how you approach 0 from the left or from the right, you had that 1 over 0 from the left is negative infinity, and 1 over 0 from the right was positive infinity. So now let's use this in the following. So what's 0 divided by infinity? You can view this as 0 multiplied by 1 over infinity. But of course, 1 over infinity is just 0. So this is 0 times 0, and then just equals to 0. So that is a determinate form. 1 over 0 again is determinate. It just depends on how we approach 0. So this is going to give me either plus or minus infinity. Finally, the infinity minus infinity turns out to also be an indeterminate form. Namely, depending on which infinity dominates the expression, you could get any real number as your answer, or the limit might actually not exist, or particularly it could be plus or minus infinity. So it's important that we recognize and distinguish the indeterminate forms from the determinate ones, because L'Hopital's rule only works in the case of indeterminate forms. If you use it for a determinate form, it will actually give you the wrong answer. So now let's look at L'Hopital's rule. So L'Hopital's rule is a very important theorem and a very powerful one, because it enables us to compute limits using a very predictable and simple technique. However, it only works under the assumptions and for the following indeterminate forms. So if you start off with two differentiable functions, that's a very important assumption, and we don't want to have the derivative of the function in the denominator be 0 on the interval about where you want to compute the limit, then if when you evaluate your limit you run into one of the following indeterminate forms, 0 over 0, infinity over infinity, and slight modifications of that, namely negative infinity over infinity, and infinity over negative infinity, and negative infinity over negative infinity. The important part are these two, the rest are just variations in terms of the signs of these two. Then what L'Hopital tells us is that we can compute the limit of the quotient f over g by computing the limit of, hopefully, the simpler expression f prime over g prime, provided the limit exists or is infinite. Now, again, two very important observations here. L'Hopital's rule must only be applied in the case 0 over 0 and infinity over infinity. You really must check that you have this indeterminate, one of these two indeterminate forms, before you can apply L'Hopital, or you get the wrong answer. And secondly, remember that it's not the quotient rule that you apply to the fraction f over g. In this case, you simply take the derivative of f and the derivative of g before computing the limit. So now let's look at some examples. Let's say we have the limit as x approaches negative 1 of x squared minus 1 over x plus 1. Again, what we do first is we try to evaluate at negative 1. So we get negative 1 squared minus 1, that's 0. And then negative 1 plus 1, that's 0 again. So we are in the case of 0 over 0, this indeterminate form where we can apply L'Hopital. So we tell the reader that we are applying L'Hopital. And now let's use the theorem. So we have the limit as x approaches -1. We take the derivative of the numerator, which is 2x, and the derivative of the denominator, namely 1. And now we note that we have a simpler form, namely one where we can compute this limit simply by evaluating. There's no more 0 over 0 hurdle, so we simply get 2 times -1 equals to -2. Looking at another example, let's say the limit as x approaches infinity of 3x squared minus 1 over 2x squared plus 1. So when I evaluate at infinity, I get 3 times infinity squared minus 1, namely infinity, over, again, 2 times infinity squared plus 1 is infinity. So again, I'm in one of the two indeterminate forms that works for L'Hopital. So let's tell the reader that I am using L'Hopital's rule. And now let's apply this theorem, namely the limit as x goes to infinity, take derivative of the numerator, namely 6x, derivative of the denominator, 4x. And before we evaluate, we can in fact cancel, namely the x with the x, and we can cancel also a 2, so I'm left with the limit of 3/2, and the limit of a constant is of course a constant, so we have that this limit is 3/2. So unlike our previous techniques, when we were not using L'Hopital, in both of these cases, we were able to understand why the answer turned out to be what it did, namely -2. Namely, in the 0 over 0 case, I was able to factor out an x plus 1 parenthesis and cancel it, and what was left over gave me the -2, but I knew that the source of the 0 over 0 came from a parenthesis of x plus 1, both in the numerator and the denominator. Here in the case of this rational function at infinity, I knew that the behavior of the function was really given to me by the leading coefficient, namely the 3 over 2. L'Hopital, on the other hand, simply gives you an answer. L'Hopital doesn't tell you, it doesn't give you an insight into why the limits turned out to be -2 and 3/2. It's simply going to give you an answer, but nevertheless it's a very powerful computational technique. So now let's look at another example. Let's say the limit as x converges to infinity of e to the x over x. So now let's try to evaluate at infinity, and it's important we remember the graph of the function e to the x. Namely, it goes through the point of coordinates 0 and 1, and it shoots up towards infinity very fast to an infinity, and as x goes to -infinity, it has this horizontal asymptote. So if I evaluate, and let's write this in quotation, e to infinity in this graph will give me, right, I'm shooting up towards infinity, so infinity, and we can also write in quotation mark, maybe we're going to use this later, what's e to -infinity? Well, that's going to be 0, because as I travel in this direction, x goes to -infinity, and the y values approach 0. So going back to our limit, what's the limit as x goes to infinity of e to the x over x? Let's plug in infinity, and I get e to infinity, which is infinity, over infinity. So I am in fact in the case of an indeterminate form that works for L'Hopital. So I can take the derivative, so the derivative of e to the x is e to the x, the derivative of x is 1, so we simply get e to infinity, which is infinity. Let's look at another example. Let's say the limit as x goes to infinity of ln of x over x. So the question now appears, what is ln of infinity? Well, let's recall its graph. It's really important you remember the graph of e to the x and the graph of ln of x. Namely, it goes to the points of coordinates 0 and 1, and it shoots up to infinity, however, very, very slowly, as it's the inverse function of e to the x. So what we have here is that ln of infinity, again I'm abusing notation of limits here, ln of infinity will in fact be infinity, and as x approaches 0 from the right, ln of x will actually approach -infinity. So that's what we can observe from the graph. So now let's use this back in our limit. What's ln of infinity? Well, we just realized that was infinity divided by infinity. So again, we get to apply L'Hopital, and we see that this is the limit as x goes to infinity. Derivative of ln of x is 1 over x. Derivative of x is 1. So we get the limit of 1 over x as x goes to infinity. And since 1 over infinity is 0, we get that this limit is 0. Another familiar limit from Calculus 1 is the limit as x goes to 0 of sine of x over x. And now we can really show with L'Hopital that the answer is 1. Well, when we plug in 0 into this expression, we get sine of 0, which is 0 over 0. So I am in the case of L'Hopital, so we'll inform the reader that I'm about to use this technique. So I get the limit as x goes to infinity, the derivative of sine is cosine, and the derivative of x is 1. So now when I evaluate at 0, I get cosine of 0, which is 1. So the idea with L'Hopital is that you can take a limit that has a, when you evaluate a hurdle, namely an indeterminate form, and upon taking the derivative, you make your expression simpler, namely you don't actually have to apply any techniques, you simply can compute this second limit by evaluating. Two important observations about L'Hopital's rule. So let's look at an example. Namely, if I have the limit as x approaches 0 of e to the x over x, well, let's take the derivative. Let's say I have the limit as x approaches 0, e to the x over 1. So this gives me e to the 0th, which happens to be 1. So this limit apparently is 1. However, that's not the case. That's wrong. Namely, the reason for that is I'm not in an indeterminate case. Here I get e to the 0th, which is 1 over 0. So we cannot apply L'Hopital's rule if we have a determinate form. So really make sure that you check, you do evaluate first that you are in fact in an indeterminate form, 0 over 0, infinity over infinity, or L'Hopital will lead you to the wrong answer. In this case, 1 over 0 tells us this division by 0 will give us an explosion to plus or minus infinity, so we are dealing with a vertical asymptote. Depending on whether I approach a 0 from the left or from the right, I will in fact get positive or negative infinity and certainly not 1. So be careful to only apply L'Hopital when you are dealing with an indeterminate form. Secondly, say I have the limit as x approaches negative infinity of say x squared over e to the negative x. So when I evaluate this expression at negative infinity, I get negative infinity squared, which is infinity, over e to the negative infinity, that's e to infinity, so infinity. So this is a classic case for L'Hopital. So let's take the derivatives. The derivative of x squared is 2x, and the derivative of e to the negative x. This is a chain rule, so the derivative of e to a power is e to that power. And then you also have to multiply with the derivative of the inside function, and the derivative of negative x is negative 1. So now what happens when I try to evaluate? I get 2 times negative infinity, that's negative infinity, and e to the negative infinity is infinity, with a minus gives me negative infinity. So I really haven't solved my problem because I just turned infinity over infinity into negative infinity over negative infinity. However, that's not really true. I've made progress, and I can apply L'Hopital multiple times until I hopefully get the answer where I can just compute my limit by evaluating. And we notice that this is the case here because if I look at the degree here in the numerator, it was 2. Now I have degree 1, so the next time I apply L'Hopital, I'm going to get the degree down to 0, and that's when I'll be able to compute the limit by evaluating. So let's apply L'Hopital one more time. The derivative of 2x is 2. The derivative of e to the negative x will pick up an extra minus, which will cancel that negative. So I just get e to the negative x. So now when I evaluate, I'm going to get 2 divided by e to infinity. The negative and the negative cancel. So 2 over infinity, which happens to be 0. So it turns out that we can apply L'Hopital more than once. If it is advantageous, and particularly it is when you can get the degrees of polynomials down until you get a constant here and there is no more x that prohibits you from evaluating your limit. Finally, we want to look at one additional indeterminate form and how to use L'Hopital to compute limits that are under this form, namely 0 times infinity. So our technique in dealing with this indeterminate form is simply going to be to rewrite one of the factors, either the one that gives you the 0 or the one that gives you to infinity, as a fraction, and that's going to turn this indeterminate form into one of the two familiar ones, 0 over 0 and infinity over infinity. That one we will know how to compute with L'Hopital. So let's look at an example. Let's say we have the limit as x approaches infinity, e to the negative x multiplied with the square root of x. If I plug infinity here, I get e to the negative infinity, which if you remember from the graph is 0, multiply with the square root of infinity, which is infinity. So I am in this case of 0 times infinity. So it makes sense for us to now rewrite one of the factors as a fraction. So I'm going to create a fraction. Now, one of them should really make sense to rewrite and the other one not. So, of course, the e to the negative x makes sense to be moved in the denominator because I get to get rid of that negative power, and the square root of x stays in the numerator. So now, if I try to evaluate, I'm going to see that I get square root of infinity, which is infinity, over e to infinity, which is infinity. So I've turned my indeterminate form of 0 times infinity into the indeterminate form infinity over infinity by simply rewriting one of the factors as in the denominator as a fraction. So now I can apply classical L'Hopital rule. So we get the limit as x goes to infinity, the derivative of square root of x is 1/2, x to the negative 1/2, and the derivative of e to the x is just e to the x. So now let's rewrite this expression algebraically. I'm going to have 1 divided, let's put the 2 in the denominator, x to the 1/2 moves in the denominator as well as square root of x, and then everything multiply with e to the x. So now if I evaluate, at infinity I have 1 over 2 square root of infinity, which is infinity, e to infinity is infinity, so I get 1 over 2 times infinity, 1 over infinity, which is just 0. So we've learned how to deal with the 3 indeterminate cases, 0 over 0, infinity over infinity. These are classic L'Hopital theorems. However, make sure you only apply L'Hopital when you are in one of these two scenarios. And then we also learn how to deal with the indeterminate form of 0 times infinity, which can be brought back to one of these forms by simply rewriting one of its factors.